Hope you're well. In this lesson we're going to be looking at something that we will call gravitational potential, then we'll be looking at gravitational potential energy, and finally we'll be looking at the escape velocity from the surface of a planet or a star indeed. So let's just go and look at the learning intentions and see what they say, and we'll pick up just round about where we left off with 4.8. So you can define gravitational potential of a point in space as the work done in moving a unit mass from infinity to that point. That's a very, very specific definition, and it's similar to the electrical potential. It's something that you should know, you should just be able to reel off, and the easiest way for you to do that is just to memorize that. So that is really, really crucial. As I say, when we're doing the actual lesson itself, I'll write it out for you. I'll get you to find it in your course notes. I'll get you to write it over various bits and pieces, but that's something that you absolutely must be able to state. 4.9, the energy required to move a mass between 2 points in a gravitational field is independent of the path taken. Well, this is the same as in an electric field, and we had a word for this. This was conservative field, so you should know that, and I know we discussed this in some depth when we were in class last year. 4.10, you can use a formula to carry out calculations with gravitational potential and gravitational potential energy, and then 4.11 are the two formulas that are involved in that. So we'll have V, which is what we're going to use to represent gravitational potential, the same as what we did with electrical potential. And finally, the last two, or last three, the last four, that would be, this is all about escape velocity. So I can define the escape velocity as the minimum velocity required. What I would generally tend to say is the minimum initial velocity required to allow a mass to escape the gravitational field to a point an infinite distance away. I can derive the relationship, velocity is equal to the square root of 2 big G big M over R. I can use an appropriate relationship to calculate calculations using said relationship, and the last one is just the same relationship as well. So here we have in 4.13 we actually have a derivation, which we don't have many of, but this is certainly one of them. Okay, well, let's begin. So first of all, we have gravitational potential, although I'm not going to start with gravitational potential at all. I'm going to start with potential energy, and technically this would be gravitational potential energy, and what we had before was gravitational potential energy, EP, was equal to mgh. Now, mass times gravitational field strength times height, and what we would have had a scenario which looked a bit like this. So we had the surface of the Earth, and we took an object and we raised it up to a certain height above the Earth's surface. And from that, if we knew the mass of the object, we would have the gravitational field strength 9.8 times the height, and we would get the gravitational field strength. And throughout all of National 5 and higher, this was fine, this works. In fact, it still does work. But there's a problem with this. When we're starting to move away from sort of Earth-based physics, and we start looking at astrophysics and planetary physics, then this really doesn't work anymore. So if we take this case and we raise it up to a certain height above the surface of the Earth, like this, that's fine, but it becomes a problem if we take this and we raise it up to a height there. So this is our mass m, And the obvious problem, I hope you've figured this out already, is that the further away that you get, than we saw from the previous lesson, if we're actually looking at what G here is, if it's on an Earth-based problem, if you're raising up 1 meter, 10 meters, even 100 meters or 1,000 meters, then we just assume that G is a constant value, it's 9.8. But if you're looking in a sort of planetary terms, if you're going to a point of say a geostationary satellite, then as you go up, then the G value decreases. G, remember, is, so G is big G m over r squared. And so as the radius, so the radius would be from here to here, your radius value is this. So as this becomes more significant, your G will decrease. And in fact, from this, if we're looking at just say planet Earth in its isolation, this would be a constant, this would be a constant. So G would be directly proportional to the inverse of radius squared. And so if we had, we would get an inverse square proportional graph that would look something like that, where you would have the G value and R value there, that as you got higher and higher, as the radius increased, it would decrease, the G value would decrease according to this. So you cannot use this formula in this equation when you're looking at planetary type of physics. So we need something else, and we need to do this in a slightly different way. Now, I will warn you, I'm not going to even go near doing this properly. I'm going to just take some shortcuts. I'm going to cheat. I'm going to probably tell you some lies, but above all else, I'm just going to try and keep it really, really simple, because it's not simple. That's the problem. The good news is that we've already come across a little bit of this in Unit 3 with the electromagnetism and the electrical potential, but just for completeness, I'm going to go through everything from the start. So if we were to have this scenario, and I'm going to just redraw this down here. So we'll have our planet. Let's just say it's Earth. The planet will have a radius. Alright, now, if we take, let's just go, so we move an object out to point P in the gravitational field of Earth. Now, at this point, we'll have a definition. So give me a second, I'm going to write this out. So we have gravitational potential is defined as the work done in moving a unit mass, so that's energy per kilogram, from infinity to that point. And so what I mean by that, and this is a subtle yet fundamental difference. Let's just say that over here we have infinity, and again, this is infinity. Well, I can't really say that infinity is going to be just sort of here. Infinity is a sort of a mathematical concept of being really far away, and however far away it is, then it's even further away than whatever you're imagining. But for our purposes, we're going to just assume that infinity is over here. So it's the work done in moving a unit mass, kilogram, from this point to this point here. Now, if you think about this in real terms and what's actually going to happen, if you have your mass or whatever and you lift it up, if we go back to our typical potential energy model, then what we had is we had our reference point. The point at which all of this was based on was that EP on the ground was equal to 0 joules. And if we raised it up a mass, then we're obviously gonna put energy into that object, and when it's held up here, it's going to store the energy, and when we release that object, that energy is then converted into kinetic energy, so that by the time it got back to its grounded reference point, the EP would be 0 joules. But there's a really crucial and fundamental difference here. The way we were looking at it now is that, well, if you take an object and you raise it up the height there, it's going to still fall back down. But if you go far enough away, in fact, if you go to an infinite distance away, well, let's just look up here. If you have an infinite distance, and remember this was just derived from our Newton's inverse square law of gravitation, which was F equals big G over R squared. If you take this radius, this distance away from the center of the object, if you take it away an infinite distance, that becomes infinitely large, and if that becomes infinitely large, then the force there must be 0. And so what's happening on a planetary scale is if you take an object and you raise it up, all the way to an infinite distance away, at infinity, the potential energy that object must have is going to be 0, because there's no force acting on it. There's going to be no force that will be experienced due to this object at this point here. And so again, if it's the work done, or if it's the amount of force, the amount of energy that it has, then at infinity, electrical potential must be 0. So we'll just write that at infinity, V is equal to 0, and we'll have joules per kilogram. Again, if you remember electrical potential, it was coulombs per kilogram, and the definition of electrical potential is the work done in moving a unit charge from infinity to that point. And so at an infinite distance away, you have 0 joules. But let's just suppose that it wasn't quite at infinity, it was just before infinity. So if it's just before infinity, the force is not quite 0, it's something, and so it's going to have an attractive force bringing it back to here. And as it comes back to here, what's going to happen is it's going to lose potential energy, and it's going to start gaining kinetic energy. And so by the time it gets to this point, it's going to have lost the maximum value that it can of potential energy and gained its maximum kinetic energy. But wait a minute, if it's losing energy the whole time as it's going towards here, if it's losing energy, but if it's started, V here is equal to 0, so if it's losing the energy, the only way that it can lose energy at 0 is if the V is always negative. And so when we look at electrical potential, not electrical potential, gravitational potential, and indeed gravitational potential energy, we're always going to be dealing with negative numbers. And this is just insane because, well, first of all, energy is a scalar, and scalars don't have negative numbers. Scalars are just a magnitude. The negative numbers would usually represent a direction. But it's okay, we can take care of all of this. The physics will work itself out in the end. And indeed, the whole idea of gravitational potential energy and gravitational potential is sort of just like a construct, a figment of a physicist's imagination. And in real life, what we're actually going to be doing is everything will sort itself out. You'll see what happens as we go on through this. So if we wanted to find what the gravitational potential of an object that was at point P, then we're gonna use calculus, which the calculus is, there's some in the course notes, but I'm not going to get into it now because it's not required for your exam. It's not required as part of this course. And what it's basically doing is it's just adapting. In fact, I'm not even going to go there. I'm just going to tell you what it is. And so, gravitational potential at a point P. So we'll have the formula, and it's just going to be V. So big V is equal to minus Gm over R. And that's it. V is measured in, I'll get this right, joules per kilogram. I was wanting to write units per kilogram, but it's joules per kilogram. So gravitational potential is measured in joules per kilogram, and the formula for V gravitational potential is just minus Gm over R. So what would we do this? And I mean, really, let's just be honest here. Let's kind of cut to the chase. For gravitational potential, what do you need to know? Well, the first thing, crucially important, is you need to remember this. You just learn it by rote. Learn it however you want. Don't care. Just learn it. So that, you need to know that. This you're given in the formula sheet, so you don't really need to learn it, but you just need to be able to use it. And to use it, well, you obviously know what G is, what big M is, what R is. You remember that V is joules per kilogram. Great. Stick numbers in, and away you go. That's it. That's all you need to know about this, and it's just, we're not going to try and overcomplicate it any further than it needs to be. So we'll do a quick work example, and then we'll start looking at gravitational potential energy. And so we have calculate the gravitational potential of a 2-ton satellite at an altitude of 20,000 kilometers above the Earth's, or above the surface of the Earth. So calculate gravitational potential. Well, we have gravitational potential being V is equal to minus G big M over R. Don't forget the minus. Big G, 6.67 times 10 to the minus 11 times mass of the Earth. Again, this can be found in the data sheet, but we're looking at 6 to the 24 times 10 to the 24. And that divided by now R. So it's 20,000 kilometers above the surface of the Earth, and so we have 20,000, which I'm just going to say 20 times 10 to the power of 6. So kilometers, 1,000, meters, 1,000, 1,000, 1,000 is a million, so times 10 to the 6. And we're going to add that on to the radius of the Earth, which is 6.4 times 10 to the power of 6. Which equals something 1.52, so let's say 1.52. Now 6 here, so it'll be 7. 1.52 times 10 to the power of 7. And that is going to be joules per kilogram. Okay, and so, sorry, minus. The easiest thing here, and you just saw me here, you've got to remember to keep the negative value, the negative number going all the way through. So it's minus 1.52 times 10 to the 7 joules per kilogram. That's the gravitational potential at a point 20,000 kilometers above the surface of the Earth. Notice the mass of the satellite is irrelevant in this case. It's the amount of energy, the amount of work done at that point in the gravitational field. It's purely independent of mass. It's the amount of work done that you would need to do to 1 kilogram to bring it from infinity to the point P. Okay. So gravitational potential energy now. We have gravitational potential as the work done in bringing the unit mass from infinity to a point in the field, and your gravitational potential, V, was defined as the joules per kilogram. So if it's joules per kilogram, if you multiply joules per kilogram by kilograms, then you'll get joules, which is what we want. And so, again, this is massively oversimplifying. So EP, we're just going to say is Vm. So gravitational potential multiplied by mass. And indeed, if we look at the learning intentions, we'll see here that EP is equal to Vm. And if we just take V, our gravitational potential, remember V is equal to minus big G over R, then just multiply that by mass, we get EP is equal to minus big G big M over R. Okay. Again, if we work through this, well, let's just do an example. So example, calculate the EP of the satellite in the previous example. So calculate the EP of the satellite in the previous example, and we have EP is equal to, we can just say Vm, but just for thoroughness, I'm going to go minus G big M over R, 6.67 times 10 to the minus 11 times the mass of the Earth, 6 times 10 to the 24 times the mass of the satellite. Now we remember our satellite was can you see it here? It was a 2-ton satellite, so 2,000 times 2,000, and it was at 20,000 kilometers, so 20 times 10 to the 6 times 6.4 times 10 to the 6. So yeah, well, we have this, which is our gravitational potential. If I multiply that by 2,000, then I'm going to get 3 to the power of 10. So minus 3, let's just go minus 3.03 times 10 to the power of 10 joules. Okay, so the amount of energy that the satellite will have at an altitude of 20,000 kilometers above the surface of the Earth is 3.03 times 10 to the 10 joules. Alrighty, now this is still crazy. I mean, we've just said that the energy of this is minus whatever. It's got less than zero energy. How can anything work? How can it do anything with that? Well, let's have our planet Earth here, and let's have our satellite here. Obviously not drawn to scale. Get the sun coming out, so we're going to get some, what's like shadows of the, I don't know, anyway, it's the dark side of the moon here. So at our point, which is 20,000 kilometers, let's go for that, 20,000 kilometers above the surface of the Earth, it will be 26.4 thousand kilometers from the center of the Earth, so that's going to be a radius value, and we've calculated that the energy, so EP at that point is equal to minus 3.03 times 10 to the 10 joules. Now, what would the potential energy be at the surface of the Earth? Okay, so the potential energy there, EP, equals, well, let's just do another calculation here, EP of the satellite on surface, and we're going to have EP is equal to minus big G big N over R and it's going to be the same number, it's just our radius is going to change, so it's just going to be 6.4 times 10 to the 6. And that's going to give us minus 1.25 times 10 to the 11. So that's going to be minus 1.25 times 10 to the minus 11 joules. Okay, so the EP here, we're going to say is minus 10 to the minus 11 joules. Alrighty, now we have an energy here, we have an energy here. We have the satellite. At one point the satellite was manufactured on Earth, and when it was on Earth As you see, it was on the space rocket about to be launched into its orbit up here. The amount of energy it has was minus 1.25 times 10 to the minus 11. The energy it has here is minus 3.03 times 10 to the, not minus 11, is it? Sorry. It has. So this amount of energy, and up here it has this amount of energy. Okay, now here's the crux of the matter. In order for you to put this satellite starting in this position to this position, you're going to have to give it energy. You're going to have to put energy. You're going to have to fire a rocket which is going to give you chemical energy, and that chemical energy is going to convert itself into potential energy. This number is a bigger number than this number. And so if it starts with this, you need to add on energy to get to that. So change in EP is going to be that one minus that one. So minus 3.03 times 10 to the 10 So we've got minus 3.03 times 10 to the 10 minus 1.25 times 10 to the 11. Now this is the clever bit. The minus turns into a plus. And if we work this out in our calculator, we'll have, I'm just going to put it in, minus 3.03 times 10 to the power of 10. We know that changes into a plus, which is okay. So 1.25 times 10 to the 11. And we get, wait a minute, that's positive. So suddenly now, if we're looking at changing potential energy, then all changes are positive. So 9.47 times 10 to the 10 joules. What this basically means is, and the crux of it is that in order to launch that satellite from the surface of the Earth up to its orbital position, 20,000 kilometers above the Earth's surface, you have to put in 9.5 times 10 to the 10 joules to the satellite. You've got to give it that amount of energy. That's the amount of work that you need to do on that satellite. And so it is still fine. It works in exactly the same way as here. As we move it up, we give it energy. We do work on it, which is stored as potential energy. And we've just done exactly the same thing here. As we raise it up off of the surface of the Earth, we're giving it energy. But we're just having a wee bit of a kind of sneaky cheat around by having it the actual values there. But all anyone really cares about is how much energy would you need to give the satellite in order to put it in that orbit, and that's your answer there. Okay, so hopefully that kind of makes sense. Again, sometimes understanding almost is overrated. You've got the formula. As long as you know the variables which you plug into the formula and you can do it, that's fine. Indeed, this is very, very similar to when we were looking at spectra and higher. When we looked at spectra and higher, we had the energies of the electron orbits around an atom, and closer to all energies there were negative, and we explained that in exactly the same thing, that as you take an electron and you move it further and further away from the nucleus, the attractive force would be less and less and less. But as you move it away, you would have to do work on it to bring it further away from the nucleus, the center. All the numbers worked out there, all the numbers will work out here. Plug numbers in and away you go. Okay. So we'll just do one other relatively quick thing, and this is looking at the EP and EK of a satellite. And so if you have, just similar before, we have a satellite that's going to be orbiting somewhere above the Earth, and it's going to be, let's just say it's moving around like this. It will have its tangential velocity, of course, will be that. And from doing satellite motion, we came up with the Newton's inverse square law of gravitation, which was well, let's do this properly. So we had Fg is equal to Fc, and then we had big G m over r squared, and our centripetal force mv squared over r. So this is our again this magical starting point in so much of this, and then what we can do is we can take out those two values, and so then we have mv squared is equal to gmm over r. Now to get kinetic energy, we half. So we want half mv squared, and that's kinetic energy there, but if we half this side, we've got to half that side, and so half g mm over r. Now, if this is EK, then that term there is going to be minus EP, because remember EP is minus big G big M over R. And so we can make a statement and say that the potential energy of this satellite and the kinetic energy of the satellite, they're related to each other, and it's a good way to calculate one or the other if we know if we know one of them, we can easily calculate the other one, because minus a half EP is going to equal the EK of a satellite. And if we were to multiply, well, I guess if we multiply through by minus 2 of this, then it would give us the same, that, well, you multiply that by minus 2, it becomes plus 1. So it's just EP is going to equal minus 2 EK. So that means that at any point that we have that the kinetic energy of a satellite is going to equal minus a half of its EP, or its EP is going to equal minus 2 times the EK of the satellite. And so, for example, in the last question we did, we had, let's see where we had calculated here. So we calculated the EP of the satellite as being minus 3.03 times 10 to the power of 10. So EP is equal to 3.03 times 10 to the 10 joules. Let me just double check that. Minus 3.3 times 10 to the power of 10. Yep. So we got minus 3.03 times 10 to the power of 10. If we know this, then the EK of this is going to be, so if we multiply that by minus a half, and so EK is going to be minus a half times minus 3.03 times 10 to the power of 10 well, we can say that's just going to be plus 1.52 times 10 to the power of 10 joules. And so for the satellite that's 20,000 kilometers above the surface of the Earth, we know that at that point it's going to have a kinetic energy of this value here. So what this means is if it gains altitude, so if it gets higher, then it's going to gain potential energy. So the potential energy is going to get greater, and if the potential energy gets greater, then it means that it will lose kinetic energy. And again, this is a sort of slightly abstract thing, but because this is negative and we've got a negative of the negative value almost, then it does all work. Just trust me on that. But here again we have this. Yeah. So if it gains altitude, it's going to gain potential energy, but it will lose kinetic energy. And if it loses altitude, it's going to lose potential energy but gain kinetic energy. So finally, we're going to look at escape velocity. So escape velocity of a satellite, of an object. What's going to happen is if I come back to the surface of the Earth and we throw a ball up in the air. As the ball travels up in the air, it's going to lose kinetic energy because it's gaining potential energy. So there's going to be that energy conversion. But as it travels up, it loses kinetic energy and therefore it loses velocity, and it will come to a point where its velocity will be zero. And at that point it will have the maximum potential energy that it has, but it won't go any further because its velocity is zero, and then it will just start to fall back to Earth. But imagine a scenario where you give it enough initial kinetic energy where it goes all the way up, and we know from earlier definitions that when it gets to a point that's an infinite distance away, then it ain't coming back anymore. So it's the theoretical initial kinetic energy that you would need to give to that object in order for it to escape the gravitational field. And escape velocity would be defined as the minimum initial velocity required to escape the gravitational field of the object that you're trying to escape from. And so if it goes from this point here to this point here, the loss of kinetic energy is equal to the gain or the change in EP. Okay, so if we look at what the change in EP is, remember you've got to be able to define this, and so this is important that pay attention. So change in EP is going to be our final value of EP, which is our EP at infinity, minus the EP and if we just say on Earth, so minus the starting EP. So the change in EP is going to be the energy at infinity minus the energy when it was on Earth. Now we know that EP in infinity is going to be 0, and that's going to be minus GMM over R. And this gives us that the change in EP must be GMM over R. And so that's kind of the first thing. It starts off here, it goes to here, the change in potential energy is going to be that. Now, what happens is that the EK here, by the time it gets to there, is turned into EP. So we can see that the EK at the start is equal to EP, or delta EP, i.e. the gain in potential energy. Whatever it's lost in kinetic energy, it must gain in potential energy here. And so we can have half mv squared is equal to gmm over r. This cancels and this cancels. Multiply by 2. So we'll have v squared is equal to 2gm over r. And then v, and we'll say escape. So v escape is equal to the square root of 2gm over r. And so that would be your escape velocity of whatever object that you have. So that's the minimum velocity required to escape the gravitational field of an object. If we think about it, the escape velocity, and if we're looking at black holes, and we'll come a bit to look at black holes a little bit later on in this course, but if the escape velocity of any object from a black hole is greater than the speed of, if the escape velocity from a planet, because if we look at this, then the actual mass of the object is irrelevant. What we have is the radius of the object, the planet or the star, and the mass of the planet star. And so if this value here is greater than the speed of light, then this is what is defined as a black hole. There's in the course notes you'll find, I think on page 68 of the course notes, there's I work out, I use density and stuff. It's not in the course at all. I'm not going to waste any sort of real time going over it, but if you want to have a look at that yourselves, then feel free. But that's the basic definition. We've got mass and radius of a star. You're not going to get a planetary black hole, but so the mass and the radius of the star, if it's in the right combination, if that value is sufficiently large enough, i.e. greater than the speed of light, you will have what would be defined as a black hole. Okay, we'll do a worked example on this, just a quick worked example, and we can have something like on Earth. So it doesn't really matter what, but we can have, let's say Chuck Norris goes to kick a football. What initial velocity would Chuck Norris have to kick a football if it was to escape the gravitational attraction of Earth? So we would have V escape from Earth, and we could have 2 big G big M R the square root, so 2 times 6.67 times 10 to the minus 11 times, so that's G, and then mass of the Earth would be 6 times 10 to the 24 over the radius of the Earth, which is 6.4 times 10 to the 6, and the square root of all of that. Which gives us 11,183. So let's call it 11 kilometers per second. So 11 kilometers per second is the escape velocity of Earth, or at the surface of the Earth. And that's it. And that, as I said before, that's independent of mass of the object. And so you could fire a rocket, you could whatever you want. It has to have an initial velocity of at least 11 kilometers per second if it was fired. And please remember that this escape velocity, the way it's defined, is a bit unrealistic, because you're not going to send a rocket to the moon or to wherever. If you wanted to send a rocket out into deep space, you're not going to fire this as a pure projectile, and this is what it is. It's a pure projectile where you give it that initial velocity and then leave it to gravity's effects for the rest of the journey up. In practice, what you're going to have to do, you're going to fire the rocket engines, and the rocket engines are going to keep firing, and it's going to accelerate as it gets higher and higher and higher and higher. So while this is a value, I guess it's kind of meaningless. Okay, right, lovely. Well, thanks for watching, and we'll see you again soon. Okay, bye now.